Today's lesson is on drawing Lewis dot structures. So we would like to first understand what these structures are for. Then we're going to go through the steps for writing Lewis dot structures. And finally, we will see how to represent a polyatomic ion with a Lewis dot structure. So basically, Lewis structures, the way that we're going to use them most often is to represent covalent bonding. So we're sharing electrons when these atoms are bonding. And you'll see in upcoming chapters that we use these Lewis dot structures to help us predict reactivity, to help us predict shape, to help us figure out what's going to mix well with something else. It'll also help us to determine the polarity of an entire molecule. So let's go through the steps. First step, we want to make sure that we count the number of valence electrons that we have to work with. So you set up a periodic table that has valence electron numbers at the top. Remember that helium only has 2. The rest of that group has 8, though we probably won't be using helium or that group very often. So if you look up nitrogen, hydrogen on that list, you'd see that nitrogen has 5. We have 1 of those, and we have 3 hydrogens, each with 1 valence electron. Our total number of valence electrons to work with is 8. So that's step 1. Count your valence electrons, write that number down. Step 2, we want to draw the skeleton of the structure. So skeleton means arrange the element symbols as the atoms will bond together. And you'll get used to knowing where to place what as we go, but generally your least electronegative element, the one capable of the most bonds, is in the middle of the structure. We would call that the central atom. And then we have the outer atoms that usually form fewer bonds or have a higher electronegativity. So we place 1 covalent bond between each of the bonding atoms, and then we update our valence count. So every time I draw a line, that's representing 1 covalent bond, and that's 2 electrons. You can see that I've connected all of the atoms that would bond together, and I've used 3 lines, so that's 2 electrons per, that's 2 times 3. 6 electrons have been used. So I've gone from 8 to 6 to 4 to 2 valence electrons. So now we're on step 4. So what we're going to do is check the outer atoms, and if any of them need more electrons in order to make a duet, to make an octet, you give them those electrons. Notice that hydrogen, helium, lithium, beryllium, and boron, the really small atoms, aren't going to need that octet because they will change their number of electrons in order to have 2 to be isoelectronic with helium. So in this case, with ammonia, the hydrogens on the outside only need 2. So this is one thing to learn about Lewis dot structures. You'll only see hydrogen single bonded to something else. You'll never see anything else within a molecule for hydrogen. It's just a bond, never put any additional dots on it. So we're going to say that this is not applicable, this step. We're just going to go to the next step for this structure. So now we add remaining valence electrons to the central atom. And it is okay to go over the octet. You'll learn more in future sections on how that is possible or why that's possible. So in this case we had 2 electrons to work with that were left over. We did not need to add any additional electrons to the hydrogens, so those last 2 electrons are placed as dots on the nitrogen. And now we're out of electrons. So now we go through our structure and we double check it to make sure that we have the appropriate octets or duets. And our central atom nitrogen is one of those elements that needs an octet. And just by circling this is just a visualization technique. I'm circling all of the bonds and the electrons directly around nitrogen, and there is 8 there. There's 2, 4, 6, 7, 8. Then for the hydrogens, again, this is a concept of overlapping orbitals between 2 atoms, and hydrogen is sharing a total of 2 electrons in this single bond with the nitrogen. And the same thing happens for the other hydrogens. So nitrogen has a duet, an octet, and the 3 hydrogens all have a duet. We've used 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. We have used the appropriate number. We didn't go over the number that we counted at the beginning, and we didn't fall under the number that we were going to use. Now, this last step we're going to see in some examples we're about to do, but if an atom needs an octet, doesn't have one, what we do is we would place the additional free pairs of electrons from adjacent bonding atoms in between those atoms to create a double covalent bond, or we might even have to bring 2 pairs of electrons in, and that would be a triple covalent bond. In this case, we already saw we had the octet and the duet, so we don't have to worry about that. That's not applicable. So what we're going to do right now is go through 3 different examples, and notice at the bottom that I have a chlorate ion. So we have 2 molecules and a polyatomic ion, and you'll see how that's different at the end. That'll address the 3rd question we had at the beginning. So the best way I think you could do this is pause at this point and do as much of the first example as you can, and check your answer with mine. And so use those steps that we just wrote down, see how well you understand them. If you need to, rewrite them in a way that makes more sense to you. So I'm going to go ahead now and start with carbon dioxide. You should pause this and finish the carbon dioxide structure as much as you can, and then come back and check with my work. Okay, so carbon dioxide, my first step is to count the number of valence electrons. And so using my periodic table, I know that carbon has 4. I know that oxygen has 2. There are 2 oxygens, and each one has 6. And so 4 and 12, I have 16 electrons to work with. Next, I place my skeletal structure, and carbon is the least electronegative element, so it's going to go in the center. Next step, I'm going to put 1 covalent bond between each of the bonding atoms and update my count. So I just put in 2 and 4 electrons. I'm down to 12. Next step, I need to complete the valence, or the octets, of the outer atoms. And remember, don't exceed your number of dots. So if you run out of dots, you run out of dots. You just stop there. Okay, at this point, taking a look at what we've done so far, the next step would be if there are any additional electrons, we would add them to the central atom. But we're out of our 16 electrons. So we go on to the next step. Now what we want to do is check to see if we have an octet or a duet for these elements. The oxygen has an octet. The carbon only has 4 though. That is not an octet. And oxygen over here has an octet. So what we need to do is make changes to this structure so that carbon also has an octet. And at the same time, we don't want to take away an octet from our oxygen atoms. So our solution is we're going to move a pair of electrons from each side, and it doesn't matter which pair you move here. I'm moving those pairs to the center, and now what you've seen I've done is we've created 2 double bonds, 2 double covalent bonds, and if we circle now to get a little bit better visual, there's 8 valence electrons there. Since each line means 2, there's 8 valence electrons around this carbon. There's 8 valence electrons around the other oxygen. So we have shared more electrons to make these double bonds. We haven't completely removed electrons. We've just shared more. And so my final Lewis dot structure, as I would draw it, looks something like this. You have some choice on where those dots are placed angle-wise, but that's it. So now I'm going to go on to nitrogen. You should pause the tape, the video, try to do as much of this as you can, and come back and check your work. Okay, so our step 1 is to add the nitrogen atoms' valence electrons together. We have 2 nitrogen atoms, and each nitrogen atom has 5 valence electrons. We have 10 valence electrons to work with in this structure. we draw the skeleton. That's step 2. We make one covalent bond here to connect our bonding atoms. Update your count. Always update your count. And now we complete the octet of outer atoms. You see I just used 6. I'm down to 2. So that means I won't be able to complete the octet for the other atom. And I'm out of dots at this point. So now if I were to check and see where I'm at, there's no central atom to add additional ones to, and we don't have any anyway. But I'm going to update my count of where I'm at. I've got 8 valence electrons around this nitrogen, so it has an octet, but the other nitrogen only has 4 valence electrons. So again, our solution here is we are going to share more valence electrons with the other nitrogen atom. If we move one pair to be shared to create a double covalent bond, you can see we still have our 8 on the nitrogen, but we only have 6 on this other nitrogen on the left. So we're going to move one more pair. This is called a triple covalent bond, and this is our limit. There is no quadruple covalent bond, only triple. And now you can see if I draw my circles, I've got 8 there because each line means 2. I've got 8 there. Both have an octet. I verify my count. I've got 2, 4, 6, 8, 10. That's how many dots I had to work with. My final structure for the nitrogen molecule looks just like that. On to our last example, and see what you can do on this one. I'm going to give you some advice in advance. When you count the number of valence electrons, you have to add in the dot, or add in the electrons due to the additional charge. So a -1 means add one more dot to your total. Okay, so here I'm doing the math that I have 7 valence from chlorine. I have 3 times 6, I have 18 from oxygen. And the -1 charge means add an additional electron. This total is 26. I draw my skeleton, and chlorine is the central element in this case. I make a single line between each of the bonding atoms, update my count, complete the octet of outer atoms. This is 18 electrons that I'm adding in. I'm down to 2. I place additional electrons on the central atom. I am totally out. I'm going to go around and inspect. I have 8 valence electrons on all of the oxygens, so they all have an octet. That's good. Chlorine also has an octet, so there's no other rearrangements that I need to do. But there is one more thing to do, because this is a polyatomic ion. We know it because it has a charge. I'm going to bracket this Lewis dot structure, and I'm going to place the charge on the outside of it. Always definitely for these negative ions do you do this kind of bracketing, and I've seen various representations where they do or don't bracket a positive polyatomic ion, so I wouldn't get too worried about that. So this pretty much wraps up the video. We learned that these Lewis dot structures are going to help us out with shapes, eventually with reactivity, with solubility. We also learned how to draw Lewis dot structures, and we learned how to represent them for molecules and for polyatomic ions.